Hello, welcome to FW563. I'm glad to be teaching analyses for managing wild populations this term, and I look forward to working with you through the course material. I'll begin with a few introductions, a brief course overview, and finish up with some introductory lecture material. My name is David Pavlaki, and I'll be your instructor for this course. My research interests include quantitative methods to answer questions in population and conservation biology. I've mainly been involved in bird population monitoring with a focus on sampling designs and estimating incomplete detection. I've studied dispersal ecology and estimated abundance and multi-scale occupancy. Some of the critters I've studied include the northern spotted owl and more recently the Australian log runner from southeastern Queensland, Australia. So I'm excited about this course material because when I took a related course in the early 2000s, the quantitative methods I learned allowed me to become a more well-rounded scientist. So it's my wish that this course material will benefit you in much the same way. I'd like students to post an introduction to the discussion forum with their name, department, what organisms you're interested in, what types of data collection protocols you're familiar with, what you'd like to get out of this class, and of course, something we can remember you by. I'd like to begin with an overview of basic population dynamics, provide a context for the tagging studies, why we do them, and get into some data collection protocols. This is a population level biology and distribution course. When we think about population biology, we're interested in things such as density dependence and population vital rates. In terms of evolutionary biology, we may be interested in life history theory or the stages that an organism travels through in their lifetime that are represented in a life table. And we're often interested in the management and conservation outcomes, where we may want to decrease populations of pests, increase populations of threatened and endangered species, meet management objectives, or study the effects of climate change on distribution and abundance. This course focuses on the estimation and modeling of population parameters, and we will cover many of the same topics presented in FW 662 and BZ 548. However, we won't study these topics in the same way. So rather than building a mathematical model that describes population dynamics, we will focus on estimating the underlying parameters that we can use to build such a mathematical model. So in other words, this is an empirical data analysis course. So here's a basic model of population dynamics where we have population size in the future represented by n at time t plus 1 equals population size in the past at time t plus births plus immigration minus deaths minus emigration. So this suggests we're interested in population size. However, we're also interested in the population vital rates for survival, reproduction, and movement. And so we are interested in predicting population size over time, but this focus on the dynamics allows us a more mechanistic understanding of how the populations change through time. Occupancy dynamics can be represented in much the same way, where we have the proportion of sites occupied in the future equals the proportion of occupied sites in the past that do not go locally extinct, plus the proportion of unoccupied sites in the past that become colonized. So this suggests we're interested in the proportion or probability of site occupancy represented by psi, or the devil's pitchfork, local extinction represented by epsilon, and colonization represented by gamma. So I'll spend a little bit of time with this model because as we move through this course, we'll become adept at representing population dynamics using probabilistic arguments. So here we have the probability of occupancy at time t plus 1 equals the probability of occupancy at time t times 1 minus the probability of local extinction. So this term represents the probability that a site does not go locally extinct. So the product of these two terms then represent the probability of occupancy at the sites that do not go locally extinct, plus 1 minus the probability of occupancy at time t represents the probability that a site is unoccupied, times the colonization rate at time t. So the product of this term represents the probability that an unoccupied site becomes colonized. So taken together, these two terms represent the occupancy dynamics through time. So why monitor and estimate population vital rates in the first place? So we often want to think very hard about the objectives for doing this type of monitoring and population estimation. And often we're interested in the conservation or management of the species, and we may want to evaluate specific management objectives, that is to determine the effectiveness of different management actions, or make state-dependent management decisions, and that is to assess the current state of the population and determine which is the best action to take based on that population state. Or we may want to learn about the ecological system in a more general way, and that is to do conservation science to increase our understanding of the ecological system. The important point here is that monitoring or population estimation is not a standalone endeavor, and we have to think hard about the objectives for doing this type of work. And of course, the context for data collection is the scientific method, where we formulate a research question based on theory and observation, develop alternative hypotheses and predictions, conduct a study design or an experimental design, collect and analyze the data, and evaluate strength of evidence for the alternative hypotheses, and we do this by comparing the predictions to the data. Inductive reasoning is an important aspect of the population modeling that we'll be doing, and that is going from the particular to the general. So when we make statistical inference from the sample to the population, this is a type of inductive reasoning. Also, developing hypotheses from a limited set of observations is also a form of inductive reasoning. So logically, there is always uncertainty in inductive inference. That is, there are no certain generalizations, but luckily, the uncertainty can be measured by statistical methods if the sample has been drawn properly and the assumptions of the method have been met. So here is a cartoon of strength of inference, and at the top we have manipulative experiments where we have treatments and controls, and where the experimental units are randomly assigned to the treatments. In the middle we have a constrained design where we may not have a control but randomization. And on the lower end, we have observational studies, which is the realm of many of our tagging studies. However, there's an important distinction to be made between a priori and a posteriori hypotheses. So when we think hard about the objectives and hypotheses and predictions, and do that up front, we limit the possibilities that we will consider on the back end of the study. In contrast, in a retrospective study with a posteriori hypotheses, we may have an infinite number of explanations for the patterns we see through a study. So the main point here is in our observational studies, we should think hard about making a priori hypotheses for this type of work. So we can strengthen inductive inference by using the method of multiple working hypotheses, where we consider multiple hypotheses simultaneously. So using this approach, we arrive at a set of competing hypotheses that are represented by models. And then we use confirmation of complementary hypotheses more than hypothetico-deductive falsification. So in this case, we don't really have a null hypothesis and use that deductive logic to falsify our hypotheses. Yet the hypothetico-deductive method is important for setting up our hypotheses and predictions. Through this approach, we identify plausible mechanisms and evaluate their relative contributions, and we do this by confronting multiple competing hypotheses with the data. And I'd like to go out on a limb here and suggest that quantitative methods and statistical theory are central to the sciences. For one thing, valid inference rests on appropriate methodology, and using these quantitative methods, we can arrive at statistical inference with measures of uncertainty. And another important aspect is this approach allows us to integrate assumptions into our inferences and provide strength of evidence for the alternative hypotheses. And importantly, we want to understand processes beyond those patterns alone.